So I'd like to get started our last panel of the day. So I will introduce our moderator of the panel, Greg Stevens, and then Greg will be introducing his panelists. Our last panel is on digital twin to transform autonomous vehicle development. Greg served as the research director of Mcity, where he steers the center's strategic research plan for next generation mobility, including connectivity, automation, AI, and the role of infrastructure. He also oversees Mcity's industry partner research program. He serves as project manager of industry and government-funded projects and directed by Mcity, and collaborates with others within Michigan Engineering to ensure effective development and execution of the research program. So one of Greg's priority at Mcity is to help translate innovative research into valuable industry applications. And I also want to add that Greg, before joining Mcity, maybe 18 months ago, Greg was the chief engineer for the ADAS system for Ford, and with 30 years of career with Ford before that. So let's welcome Greg.
Thanks, everyone. What we wanted to do to get started here is set a little context on digital twinning and what we're going to be talking about for the next hour. Calvin, could you go forward?
Yes.
Oh, right there.
Yeah.
You're very quiet. Okay, so this is our open source digital twin of our Mcity Proving Ground. This one is in Carla. You can see the level of detail that it's been rendered at. And the QR code that's on the top on the left there, it takes you directly to our GitHub, where you can get full access to our digital twin of the track. And the great thing is it's released under an MIT license, which basically means you can take it and use it, modify it, resell it if you want. You can do anything you want. You just can't sue us, okay? That's the only limitation. And then the one underneath is a QR code for NVIDIA Cosmos. And the reason that's there, you know, in the panel discussion this morning, they brought it up, right? This idea of having a physical, realistic underpinning that you put a generative model on top of, right? And so that's exactly what we're doing with NVIDIA. Darian's been hard at work making our Carla digital twin here into an Omniverse digital twin, and then we're going to be using Cosmos on top of that to do the generative work of creating snow or bad weather or things like that, to sort of paint over the physical basis, which is held in Omniverse. And if you go to the next slide, I like to tie everything we do back in some way to AI, because that's really the defining technology of the moment we're in, right? And so I have up here, you know, our AI data engine that we use at Mcity, where you basically start from an AI model. You test it out at Mcity 2 in our track, in our mixed reality environment, deploy it into the real world, find places it doesn't work well, find training images, auto-label those images into your new training data set, retrain, retest, redeploy, you know, do that in an iterative loop. And so then what we're going to talk a lot about in this panel is how does a digital twin help with this? So, you know, one of the first topics and one of the things that Katie Washabaugh is well-versed to talk about is synthetic data generation. So once you have an Omniverse model and you have the NVIDIA high-fidelity sensor models, you can use that for very high-fidelity, realistic data generation that you can then use to supplement your training databases to get diversity to retrain your models. Mixed reality testing, this is something Darian can speak a lot about, because Darian's sort of the chief creative lead of our digital twin work at Mcity. And think of mixed reality as you have the physical track and you have a physical vehicle on the track, and you overlay the digital twin as a layer right on top of that. And then you have the vehicle set up so that it can see everything in the physical world and in the digital world simultaneously. So then we can insert obstacles into the digital world that the physical vehicle on the track will see and will react to. And then the last one, which Katie Skinner can talk a lot about, is some work we're doing using digital twins and Gaussian splat models actually to make real-time digital twins. So to take real-time sensor data, form it into a world model in Gaussian splatting, including all the dynamic obstacles moving through the scene, and then use that online as the input for your planning model. And so that's the context. Next, we're going to have each of our panelists introduce themselves, their background. Then after that, I will ask some moderated questions, and then we're going to open it up to everybody here in the audience. So be thinking now about what question you want to ask. And do we have online questions as well? Yeah? No? Okay, maybe. If it is online, feel free to type them into the chat and we'll try and take a look at them. So with that, why don't we just start here? Katie Washabaugh.
This is where, oh, there we go. Right, so as Greg mentioned, my name is Katie Washabaugh, and I am the product marketing manager for autonomous vehicle simulation at NVIDIA, which is a mouthful and a long way of saying that I work with our product and engineering teams to help bring our solutions for AV simulation to market. Specifically, what we're working on with Mcity is our Omniverse blueprint for autonomous vehicle simulation, which is a reference workflow that packages up all of our rendering and physically based simulation technologies into APIs and services that companies and developers can plug into their existing workflows. So we have what we call the sensor RTX APIs, which render out physically based sensor data. We have our AV Sim enhancement service, which provides all the behavior, physics, and animation. So developers are able to kind of take what they need and enhance their simulations.
My name is Darian Hogue. I'm on the engineering team here at Mcity. My background is mainly in software development and simulation. At Mcity, my role is I lead the digital twin project. So that's working with our art team for the assets that we were creating for the digital twin, validating those assets using real-world data like point cloud and RGB camera data. Also making sure that we can bring our digital twin into different ecosystems like Carla or Omniverse, and making it accessible to all students, researchers, companies. And then I also help teams and students I onboard them to how to use our digital twin and get them started for all of their testing use cases.
Hi, I'm Katie Skinner. I'm an assistant professor in robotics at University of Michigan, where I direct the field robotics group. Our research focuses on sensing, perception, and machine learning for robots in a wide range of applications, from marine and space robotics to autonomous vehicles. We have a project right now with Mcity focused on warehouse autonomy, which is a really interesting use case. So for warehouse autonomy, we have a relatively constrained environment, so we can think about putting high-end sensors on infrastructure and then have low-cost sensors on vehicles that are moving throughout the warehouse. And for that project, we're developing new models like Gaussian splatting that Greg mentioned to enable us to learn how to represent the environment and things moving in the environment to a really high fidelity model. And with that high fidelity model, we can then plan paths for vehicles moving in the warehouse to perform safe navigation throughout that space.
Okay, thanks. So Darian, let me start with you. for people who've been around for a while, like I have, you know, we tend to think of like digital twins as something that we've been doing for like 2 decades, right? You know, and it really feels like something is changing now, right? And I'm really interested in your perspective as a maker of digital twins, you know, to share with us, you know, what you've seen in the last couple years in terms of what's changed, and maybe even some of the things that are coming that you're really excited about.
So some things that I've seen change is mainly just lowering the barrier to creating a digital twin. So before it was a lot of manual work. So looking at your CAD drawings and getting an artist or yourself to create a 3D model, wrap it in a material, place it into your digital twin, and validate it. So that process can be really time consuming. There are a lot of technology and tools that streamlines that. So for instance, you can use like NeRFs or Gaussian splats to quickly recreate a 3D environment using like 2D images. So if your vehicle is fixed with cameras and you can drive through an environment and then recreate that environment using those methods. Or if you wanted to create like, let's say you have a new asset you want to bring into your digital twin, there's applications on your phones that you could take photos of and then use Gaussian splat to at least get a start with that 3D model and then bring that into your 3D application of choice and build on top of that. You also have models that Katie will be talking about, like Cosmos, that helps increase the fidelity of the NeRF output that you're going to get. So sometimes it can be a little fuzzy. You can enhance it using their tooling. And then overall, just evolution of graphics. So we have a ton of great consumer graphic cards now, and then enterprise cards that allows developers like myself to push the limits on the fidelity and the photorealism of our digital twins. So all these things make it really easy to create what you need for your use case.
Thanks, Darren. Katie, Katie. So you work a lot with autonomous vehicles and vehicle companies, and there's this transition we've talked about of, going from the very modular stack of AV software to an end-to-end stack. And how has that transition influenced the need for things like digital twins and sensor simulation?
Yeah, it's pretty interesting because we're seeing this shift around the same time these digital twin technologies are really starting to mature, as Darian was talking about, with kind of the AV 1.0 or the more modular architectures. You could kind of pinpoint data to specific parts of the stack. So you could use object level simulation for perception rather than kind of having a fully rendered scene. But now with AV 2.0, where we're using these end-to-end models, which kind of map the sensor data directly to driving actions, we need to be able to represent the world as the vehicle will experience it as it drives. And the limitations of real-world data collection kind of emphasize the need for simulation, because driving around in the real world, we won't be able to capture the number of miles or the diversity of scenarios needed to really test and validate this technology. So with Omniverse and now with Cosmos, which I can dive into a little bit more, we're able to enable this physically based simulation where we can render camera, radar, LiDAR exactly as the vehicle would experience it in the real world. And then using World Foundation models, which kind of really sprang up in the past year, we can layer on that diversity of weather, of lighting, of different geolocations to kind of cover and address the gaps that we haven't been able to fill with real-world data collection.
All right, Katie Skinner. So, when we started the Depot Autonomy project, you had lots of different options for what technologies to use for making your real-time world models. Maybe sort of take us through some of your thought process and how you got to where you are with Gaussian splat models.
Sure. So I work generally in mapping and navigation for robotics. So of course, mapping is a really large field within robotics. And in recent years, there have been some really exciting developments coming out of the computer vision community in particular in how we can learn new representations from real data. So like neural radiance fields, or NERFs, that we've been mentioning, are a way to take camera data, learn from that data to have a learned representation of the scene. What's really exciting about these learned models is that you can actually query them from different locations and perform novel view synthesis, so you can actually render images from viewpoints that you didn't see in the training data. So this is a really powerful tool. There's a lot of other things that you can do with this, like scene editing, that are also a big focus. But one of the downsides of NERF models has been their efficiency. So Gaussian splatting is kind of a newer model that allows us to render novel viewpoints and learn really dense models of the scene, but now we also gain really efficient rendering capabilities as well. So in computer vision, the focus has really been on images, and in robotics, we're now looking to develop these models for different types of sensors like LiDAR, and with the Depot Autonomy project, we're thinking about how do we handle dynamic objects in the scene as well, right? Because in robotics, we're moving around in the world, and we need to be able to represent things in our scene like humans that might be walking in our path too.
Okay, thanks. Maybe we could just go through and talk about like what we're excited about, next steps, what's coming, and then at that point, then maybe we'll open it up for questions from the audience. So be thinking of your questions. But let's start with you, Katie. What are the next great things coming from NVIDIA that are going to blow our minds?
Okay, so now I can dive into Cosmos.
Yeah.
Yeah, so as I mentioned, World Foundation models have really sort of blown up in the past year, and these are neural networks that are able to simulate real-world environments and predict future states based on text, image, or video prompts. These models are able to represent and simulate real-world dynamics such as motion, force, spatial relationships based off of sensor data. So in the case of AV simulation, we have our Cosmos Transfer World Foundation model, which is a generative model that takes in the sensor data that we've rendered in Omniverse and then outputs new conditions based on text prompts. So we can take a simulated environment of the Mcity test track on a sunny day, the car's driving, and you can type in snowy, windy, night conditions, and Cosmos can then render that over the scene. And we've turned one scenario into a completely different one. And so this allows us to really scale out testing based on a single drive. You can cover a whole range of conditions the car needs to be able to handle. So this is just one use case we've applied Cosmos to in the AV simulation space. I think there are a whole swath of areas that we haven't even touched yet. So it's a really exciting time to kind of advance this technology and see how we can really speed up different testing and validation processes.
All right, how about you, Darren? What's coming that you're interested in?
Yeah, so there's a ton of things that I'm excited about, but I'll keep it short. So I'm a gamer, so I really love high level graphics, high fidelity graphics. So the next step for me is to make sure that our digital twin is as realistic as possible. So whether that is creating 8K maps for all the textures inside the digital twin, overlaying it with Cosmos, increase the fidelity. My end goal is to have a photo of our digital twin and a photo of the real track and show anyone and they can't tell the difference. So that's something I'm extremely excited for. And then next would be continue working with NVIDIA and their Cosmos model. I would like a user to be able to prompt, for Mcity, like pretty easily to get any different scenarios that they may want for our digital twin and download that for their testing. And lastly, I would like to create like a VR, AR experience that's plug and play for our digital twin. Technically, if you're a developer, you can create your own custom VR experience, but I would like to support that out of the box with our digital twin so anyone could use that for their testing.
Yeah, maybe more of the robotics perspective. So I've been really excited about training from simulation. This has been a hot topic in robotics for several years now. But one of the main problems has really been photorealism of the scenes that we have. There's what we call the sim to real gap, that if we train in simulation and test on real data, there's going to be a decrease in performance because of that gap in realism from the simulated data that we're training on. So I think some of these newer AI models really give us a way to do, real to sim to real, where we're using real data to create simulated models and digital twins that we can then use to generate training data. And as Katie mentioned, we can augment this with things that we haven't seen in the original data that we collected, like snowy scenes, so different weather. I'm really excited about being able to model maybe different sensing modalities than we had access to at data collection time. So I'm really curious to see kind of how this pushes forward improvements in AI models if we can train on this new type of data.
Okay, great. Now for the audience participation part. Questions from the audience?
So you're able to create these digital twins of these environments, but what are some ways that you're able to populate the digital twin with simulated traffic or other vehicles or pedestrians?
Darian, you want to talk about TerraSim?
Yeah. So the Michigan Traffic Lab, they have a system called TerraSim. So you could, if you were using this technology, you would be able to load the digital twin with vehicles or agents that could follow your Eagle vehicle around and give it these corner cases that it's really hard to find in the real world. So I'm not super familiar with the implementation of TerraSim, but from internally what our research team has been using it for, they use our digital twin to give their Eagle vehicle these edge cases so that you can train it on the edge cases that you may not get in the real world.
Yeah.
And just to add on that too, with Cosmos you can add, you can prompt vegetation, so create a tree-lined street, which before you would need artists to render out all of those assets and add them into the scene. Now we're able to kind of generate them or use prompt-based generation, which really speeds up the process of kind of building out these simulation scenarios.
And I guess the thing I would add is one of the things that the Michigan Traffic Lab has done really well, I think, is training AI background agents, to have artificial intelligence to figure out what would be the most aggressive, stress-creating thing I could do at this moment to test this AV. So that's what I think is really interesting in their approach is using AI to stress test AI, right? And it can be expanded from just background vehicles that do aggressive close cut-ins at the worst possible moment to making also the entire environment can be adversarial, right? And now it can start raining, and then the rain can freeze, and then the stoplight can go to the yellow phase at the worst possible time, and then a scooter could come out, So all of this, could be, built into behavioral models that all of the infrastructure, the weather, all the other vulnerable road users, all the other vehicles could have to effectively conspire to, create these corner cases, these edge cases, and to really stress test the AV stack. Because, people like to talk about, a benchmark of humans drive 100 million miles between fatal accidents, right? So an AV should be able to, but most of that driving is really, really boring driving, right? And simulating all that really boring driving doesn't do any good, right? There's no useful knowledge that comes out of that. So, what TerraSim does is it basically condenses all of that into, 10,000 miles of really, really terrible moments, right? And if you can survive that, then they can show that that's equivalent to the same sort of adversity you'd see over 100 million miles of normal driving. So I think that's a really important efficiency improvement. Other questions?
I think this question is specifically I wanted to ask to Darian. So the Mcity digital twin that was displayed, I wanted to ask a two-part question. One, so when you mentioned that this would be an open source licensable, usable asset, so how, I wanted to know, is there any specific documentation on how exactly you have built? So did you use the same conventional method of building 3D assets on Blender and then importing them into Unreal and then building them and validating the entire digital twin as a whole, or did you use any specific newer methods to create this digital twin? And the second part was, if anyone was to build an entire digital twin, what are the newer methods that you have used that people could incorporate for validating or verifying the entire fidelity of the digital twin?
Yeah. So when it comes to your first question, the way we validate the digital twin and how we created the digital twin, we used a mix of reference images. So we have, camera data that we used, point cloud data that we collected on the track, and then we use that point cloud data to help us place the assets, manually place the assets in the scene. So for instance, to validate that, once we had our digital twin up and running, we brought that digital twin into Omniverse, and we got a simulated LiDAR point cloud scan of the entire track. We also have a physical point cloud collection that we had of the track, and we brought both of those collections into a software called Cloud Compare. And once we did that, we made sure that the scale of the digital twin and the physical track, the orientation of like the individual assets, were as accurate as we can make it. There's some areas that we are still working on, so it is a work in process to get that realism score. So we don't technically have that yet. We're still working on that. But the way we do that is gather as much physical, like real-world data that we can, and then do the similar collection in the simulated world, and then compare it with different applications. And then what was your second question? Yeah, so you can compare your point cloud data if you get collected in the sim world and the real world. There's another method that I'm still familiarizing myself with. Basically, you drive the same path that you would in the real world and in the physical world, and you have the cameras placed in the same orientation in the sim world and the physical world, and then you can compare each frame of that run, or that scenario run, using different APIs to compare that. But we're still working on that, so I haven't done that yet.
Yeah, and one thing I could add to that, we can do it as a group as well, because this is an open source, GitHub repo. And right now, if you go to GitHub, what you'll see is our Carla digital twin. Darian and Katie and NVIDIA are hard at work on the Omniverse digital twin. When we get that one to the point where we like it, we will also put that one up. We also happen to be working with Parallel Domain, so there'll be another digital twin released. But then on top of that, we're going to release all the data scans that we've done as well. So you'll be able to see LiDAR point clouds and camera data directly from the track. And then another thing we're doing with NVIDIA is we're using their high fidelity sensor models to, like Darian said, drive the exact same route on the track in digital world using the high fidelity sensor models as we drove in the real world with the real models. And so we're going to release that data open source as well. So everybody can go in and take a look and compare. And one of the things that is my hope is that people will, and that they'll say, I found a spot where it doesn't match well. So clearly either your radar model needs to be tuned somehow, or the material properties on some assets need to be changed, right? I mean, that's really one of the benefits of doing this open source, right, is that we can leverage a community to work on it. Okay, another question?
Yeah, I have a maybe challenging question, because you guys mentioned there is an issue still with the sim to real gap, right? So after all, in the simulation software, you reproduce all the vision, all the sensors, but there are still physical kind of elements which are not reproduced. So Darren, you mentioned you're a gamer actually. Have you seen the movie Gran Turismo? Okay, so then you will understand what I'm talking about. In that case, you know, someone had this great idea that a gamer who spent all these days just playing in video games, Gran Turismo, can be a race car driver, okay? Which honestly sounds a crazy idea, but it's a real life story. It actually happened, okay? There was a guy who won Le Mans, such that you know, most of his training was actually as a gamer. Yet, of course, he had to go through a very, very rigorous race car training. So my question is, what do you think we kind of still need to make that connection, right? I mean, after all, it's a digital twin, it's not reality. So what is really missing, okay, if I want to be playing Gran Turismo in Mcity?
So I can maybe take that. So first, I think that's a great example. Maybe I can use it in my classes for sim to real. But I think that the progress can come from both sides, right? We're going to need to make progress in simulation to have photorealistic simulators, but then we also need progress in machine learning, because, you know, it's never going to be perfect, right? You're never going to match everything. So we need to develop machine learning methods that are robust to some of these differences that are inevitable, right? So it needs to come from both sides.
Thank you.
And just to add on that also, in the case of AV training, we kind of think of data as a pyramid, and at the top is real world data collection. Like, we will always still need real world data for training and validation, but with simulation, we're able to scale out that data. And now, with the addition of Cosmos 2, we can replay those real world scenarios in simulation and then layer on greater data diversity. So from our perspective, we don't see the need for real world data going away, but we will be able to do more with it.
Thank you.
One other aspect is we have one of our partners at Mcity is VI Grade, and they've donated a simulator to us. It's a static-based simulator, but it, you know, is a full cockpit, steering wheel, pedals, and we're next week getting the virtual reality goggles, so you'll be able to be in the immersive digital twin driving around in the simulator. And then one of the advanced things that we're doing with VI Grade right now is we're working to hook up, you know, all of our digital twin as well as actually our physical test vehicles to the sim center that they run in Novi, Michigan. And so there they have a full motion simulator, which, you know, they use for racing development. And so in the future, you'll actually be able to go to the Novi Sim Center and sit in their simulator and drive in the digital world at Mcity, but we're also hooking it up so that you could actually do mixed reality testing at Mcity, where you would be controlling not only the digital vehicle in the digital world, but actually the physical vehicle on the physical track as well. So that'll be a really interesting upgrade to our capabilities.
Yeah, that sounds very exciting.
Yeah.
Thank you.
Thank you.
Hi, I have two questions. So the first is, when you look back, so what is the biggest challenge you faced to build this amazing scenario? And the second question is, how do you balance the photorealistic and the performance?
The first question, do you mean challenges for sim to real in the past?
I mean, building this MCT thing.
Oh, so we right now are focusing on the warehouse autonomy problem. So we have actually built or we're currently building a real warehouse environment at Mcity. So we're going to have essentially a lab environment where we have infrastructure sensors and vehicle sensors. And then at the same time, we're building the digital twin as well so that we can develop some of the Gaussian splatting models within the digital twin space. So one thing we're looking at right now that has been a real challenge is modeling dynamic objects. So that's something that's really important if we're moving vehicles around humans, right? We need to be able to also model the humans and maybe predict where they're going to go. But this is kind of an open problem in this space. So humans are hard because they're deformable, unpredictable sometimes too, right? So this is something that we're actively working on, is the dynamic objects.
And from my side, the biggest challenges that I had as a developer was the coordination with like our art team. Like working with these assets is kind of complicated sometimes, making sure they're as accurate as we can make it. And then also just validating the assets and making sure they're as close as possible to the real world. And then lastly would be making sure that our OpenDrive format, our OpenDrive road network, matches what we have on the test track. So if you're familiar with Mcity's test track, there's a lot of weird bends and turns. When you add that to like MathWorks Roadrunner, which is the platform we use, sometimes it can be a little complicated to make sure the road networks match what we have at Mcity. And then when it comes to the leverage, for performance, when it comes to the photorealism of the digital twin, our goal is we're going to have the highest fidelity version of our digital twin available. But for instance, if you're a user that does not have a 4080 or like a 5000 series GPU or like an enterprise GPU, then we're also going to release a lower fidelity model as well so that you can run it on your machine. Because I've had moments where I cranked it all the way up and then it's running at 2 frames a second and you can't really do anything with that. So we're keeping that in mind to make sure we give the highest fidelity available. So if you have the graphics that run it, you can. If not, you can use like a lower res version and still get some of your testing done.
And maybe Katie Washbaugh, maybe like a comment on parallel domains approach and maybe contrasted to taking, you know, a omniverse mesh and making it photorealistic with Cosmos, right? That's sort of like two other paths to photorealism.
Yeah, exactly. And there are a variety of ways to generate these simulations, and you know, you can kind of render it out asset by asset and kind of build it from the ground up. You can take in real world driving data and replay it in simulation. All of these different methods are great kind of base layers to then build on top with world foundation models, as long as it's all grounded in real world physics. Then we can kind of scale everything out and address these pain points that have existed in simulation for so long without having to kind of like painstakingly build these worlds.
Yeah, and our partner Parallel Domain has shown, I think Darian, you've probably seen some of the initial work they've done, and you know, the one we showed you in Carla, you could still tell that that wasn't the real world, right? It wasn't photorealistic. It's very, very realistic, but not photorealistic. But you know, the stuff we've started seeing back from Parallel Domain takes the photorealism to the next level. So we're sort of excited to get that one made as well and release that open source in addition.
Thank you.
Any other questions in the room?
I have a question related with the application of the digital twin. I think we talk a lot about in terms of utilizing the software to create a digital twin, particularly the Mcity digital twin, including both the static and also the dynamic objects. And I think I'm hoping the panel can spell a little bit in terms of how people can utilize these digital twin tools to help them with various applications. What are the applications you have in your mind in terms of these tools can help?
Who wants to go?
I think kind of the most clear-cut application for these types of simulations are edge cases for A/B testing and validation. There are so many unpredictable things that can happen when you're driving on the road. I'm sure you've all experienced some weird stuff out there, whether it's a deer running in front of your car or air conditioning units falling from apartments onto the street. These cars need to be able to react to anything and everything that can happen. And it's nearly impossible to collect that in the real world. So with these digital twins and with the simulation technology, we can model these edge cases and really robustly test and validate the car in simulation.
And for the Mcity digital twin, the reason why it's so valuable is that not only you can test in a simulated environment using our Mcity digital twin, but once you run those scenarios there, you can work with our team and book some track time and run those same use cases in the real track and then validate those scenarios that you saw in the simulated environment. So some issues that I saw in simulation world is that a lot of the times you're testing on fake cities, fake towns, right? And you're saying, okay, this is great, this works, now you're going to deploy it. So before you deploy it, you can run it the same scenario in the simulated world that you were testing in originally. If you just contact us, you can book that track time, and we'll have our test engineers work with you, and we'll get everything set up so you can run the same test in a physical way.
Yeah, and one of the things way back in the beginning when I hired into Ford Motor Company that they really impressed upon me was that proving grounds are a safe place to do unsafe things, right? Because we as engineers need to do unsafe things, right? Because unsafe things, like Katie said, will happen in the real world, and we need to know how our systems are going to react. Digital twins now are, also a very good, safe place to do unsafe things, right? And, I think, all those edge cases can very safely be handled, in the digital world without anybody getting hurt. But there's a sort of mixed reality area also that I'm really excited about, which is if you think about some of these features like, at what's called SAE Level 3 autonomy, where the driver gets to do something else, but if the AV says they need them back, they have to re-engage. If you think about that as a human factors challenge, right, that's tremendously daunting, right? Thinking about somebody who's completely checked out, they're texting or they're watching a movie, and now all of a sudden there's some sort of quasi-emergency. They have to look back up, the system's telling them to re-engage, they have to take over. I think it is a very open research question how to do that effectively. How do you do that so that it actually increases safety and doesn't result in somebody panicking and doing something even worse, right? And so the scenario that I'm really interested in testing comes from an example that Waymo published at one point where they showed a video of a pickup truck driving in front of the Waymo vehicle, and a gas grill drops out of the back of the pickup truck right into the middle of the road, right in the Waymo vehicle's path, right? And Waymo's a level 4 vehicle, so it brakes and it does a lane change, right? But imagine if that was a level 3 vehicle, right? Remember the context of a level 3 vehicle is it doesn't have all the sensors that Waymo has. It's not quite as smart as a Waymo vehicle because it's depending on the driver to re-engage in some of these scenarios. So how does that happen, right? That's a realistic scenario for a level 3 vehicle that everybody is committed to making. How are they going to handle that situation, right? I think that's a very open research question. And what I've been looking at is, how do we do that safely, right? Because we can't put real customers in real vehicles and take them out on the real road and drop gas grills in front of them and see how they react, right? That's far too dangerous. We can't even do that on a test track because that's far too dangerous. But think about what we've created here in a mixed reality environment coupled with the driving simulator we have. Now what we can do is we can take, you know, members of the general public who are not engineers, who don't understand how level 3 features work. We can put them in our simulator with the steering wheel and the pedals and put the virtual reality goggles on. We can have them drive around the track and drive not only the digital vehicle that they can see in their goggles around the digital track, but also drive a real vehicle around the real Mcity track so that they get the sense of realism, right? That they're actually controlling a vehicle. And then once, you know, they get comfortable with that, you say, okay, we'll put it in level 3 mode, so now you can watch a movie, right? They watch a movie, vehicle drives some more. Then we do, in the digital world, the pickup truck drops the gas grill on the road, and we can study how people react to that, right? The buzzers go off, a voice says re-engage now, the center cluster starts flashing or something, right? How do they react, you know? Is a safe transition possible in those kind of scenarios, right? I think that's tremendously interesting human factors work that now we can do safely because we've put together the entire tool chain to get that done. So I think that's one of the areas that I'm super interested in exploring.
We do have one question online. How's the newly developed tools and processes like 3DGS, NERFs, integrated with widely accepted simulators like Carla and Unity, since these simulators are mesh-based and are not dynamically updated?
Yeah, so I would say, you know, this is one of the benefits of having open source tools, right? There is a lot of people always working on these problems. So there have been some, you know, tools and software packages that have come out kind of integrating 3DGS into some of these simulation platforms. So I think this is one of the benefits to having those models available.
Yeah, and to build on that, we are in the process of integrating the Omniverse blueprint into Carla to make all of these technologies available to the open source community.
But Katie Skinner, you know, choosing between a 3D Gaussian splatting model for some applications versus mesh-based models for other applications, I mean, right now that's a choice. In the future, is that still going to be a choice, or does it come together somehow?
Well, I think as engineers, it's always a trade-off, right? So there's always a choice depending on your application. I think for us, 3D Gaussian splatting is really has a lot of potential because we can do things like novel view rendering and get really high fidelity images or LiDAR scans synthetically from the Gaussian splatting models. So that's kind of one of the main draws of that approach. And we also have work now integrating Gaussian splatting. We're working to integrate that with robot path planning as well. And the integration there can allow us to go from, maybe not end to end, not fully modular, but thinking about how we can have perception pipeline, planning pipeline, and trading those off intelligently.
Okay. We have reached the end of the questions, so with that, I think we could probably move to the next slot. Okay. Thank you, everyone.